we've seen mushrooms, we've seen birds, we've seen trees and animation, sports, a lot of things, but we've still been on Earth the whole time. So we'll move out of this world for the last speaker, and George will tell us about how data is reshaping astronomy.
Thank you. We are actually working on replacing live speakers, but it's another story. So it will not be a surprise to you that astronomy, like any other science today, is being completely transformed by computing and progress in information technology. And over the last 20 years, astronomy has become enormously data-rich. Today, most of the data come from large digital sky surveys, and typically today we generate tens of terabytes of data per night, which is more than the content of the Library of Congress every day. And this continues. The data volumes and data rates increase exponentially according to the Moore's law, for the simple reason that devices that generate the data obey Moore's law. Now everybody says, sure, it doubles every year and a half, but what does this really mean? It means that in next year and a half, we'll generate as much data as in all of the past history. Think about that. And so how do we actually extract knowledge from this? I'll show you some comparison numbers at the bottom. They're actually quite stunning. Now, as far as the human memory capacity is concerned, those estimates vary by several orders of magnitude. But I can totally believe that my laptop can remember a lot more than I can. So this is going to get much more dramatic in years to come. There are large sky surveys are now being developed, both in visible light and radio and so on. You can see the numbers for yourselves. But this exponential data flood will continue. And it will enable a great deal of new science, but it also poses interesting new challenges, how to actually extract knowledge from this mass of data. Let me just illustrate this for you. This is a picture of a tiny segment of the galactic bulge. And the zoom in shows you again just a little piece, and every pixel on that picture contains at least one, usually more stars. For every one of them, we would measure hundreds of numbers in any sky survey today, and then you combine them from different wavelengths. And so we're dealing with billions of data vectors in hundreds or thousands of dimensions. And that is typically how things are happening today. A more interesting part is that the universe looks different at different wavelengths. We now collect the data from radio through gamma rays and everything in between, and neutrinos, and now even gravitational waves. And different phenomena in the universe emit their energy in different parts. So if you take images in any given wavelength regime, visible, say, you're getting a biased picture of what's out there. But now we have means of collecting information across the full spectrum of the electromagnetic radiation and then some. And the data fusion becomes an important part of the scientific discovery, because there is knowledge present in the data that is not recognizable in any one data set separately, but becomes discoverable once you do the proper data fusion and data mining. So in theory, we also changed the way we do business. This is a simulation of a galaxy formation. Lots of those are happening today, a lot of high-performance computing. They involve tens, if not 100 billions of stars, galaxies, dark matter particles, and what have you. And the interesting point is that these phenomena do not have analytical representation. Not that we don't know how to do it. They a priori don't have analytical representation. There is no formula for galaxy formation. There is no formula for star formation or explosions of supernovae or anything like that. The elements of those simulations have formulas, Newton's laws or what have you. But together, you cannot write them analytically. So now the output of theory is a data set. Computed data, not measured data. Nevertheless, a data set, not a formula. This is a different way of doing theory, which is no less rigorous than the analytical approach. It complements, it lets us do things that we cannot do otherwise. So over the last 20 years, astronomy transitioned from data poverty to this exponential embarrassment of riches. And so does every other science. And all of that was enabled entirely by the progress of computing information technology. VLSI integration gave us also our detector, CCD. There is Carver Mead right there. There is Moore's law describing the increase in data volumes and data rates, because As Caltech alums, you know that derivative of an exponential is also an exponential. And in the end, we observe the universe in the computer. The archive is the new sky, and the algorithm is the new instrument. You can now make first-rate astronomical discoveries and never see telescope in your life. And people do so. Now, Caltech was always the leading institution in astronomy since George Ellery Hale started the whole business here. And our business model was always to be owners of the world's biggest telescopes. So last 20 years, I've been doing my best to undermine our business model. And in fact, I think this is probably the most important thing that we've done, that now anybody anywhere with an internet connection has the same level playing field as we at Caltech. So this is roughly the timeline how things happen. The Moore's law says that we'll increase data volume every 5 years or thereabouts. And indeed, in the 1980s, astronomers adopted digital detectors, CCDs, and helped develop them. We went from megabyte data sets to gigabyte data sets. When digital sky surveys came by in early to mid-90s, went to terabytes. We're now into petabytes. Exabytes are coming. As we went along, new kinds of technologies started being used. Image processing and pipelines, and now data and databases when we got into terascale regime and machine learning, and now very much into artificial intelligence, and who knows what comes next. But a lot more interesting than the data volume or data rates is the increase in data complexity and informational content of the data. How do we actually discover things that are totally non-obvious? It's not just there's a lot of data, but the data are simply too complex for human mind to understand unaided. So our first response to this was formation of what we call Virtual Observatory framework, which was born here. 16 years ago, we had foundational conference on the subject. Within a couple of years, this became a worldwide movement. Basically, the idea was to unify, interoperate all the data sources, archives from space missions, from observatories, etc., provide tools for their analysis, and ingest all of the data and let people do one-stop shopping, basically do nothing all day but sit in my computer and all my data and friends and theory and so on are behind it. So this became a global thing, and now essentially all of the astronomical data worldwide are accessible through an interconnected network of archives and tools and so on. And astronomy, to my never-ending amazement, is the envy of many other disciplines. And I'm amazed because I know how that sausage was made. So what happened then, we now decided to broaden community of both users and contributors. 6 years ago, we had foundational conference of the new field of astroinformatics. And the idea is to serve as a bridge, of course, between astronomy and applied in computer science and statistics and so on, but also to include this broader community, not just few experts on databases and whatnot, but students, postdocs, everyone, to write new algorithms, to share them, and also to serve as a good arena to connect with other fields, bioinformatics, geoinformatics, all other X-informatics that people work on. Because at some point, we're all trying to solve very similar problems. Now, let me give you some practical examples. Digital sky surveys, synoptic sky surveys, are the biggest source of data, data in astronomy and will continue to be so. We have not one, but two of those, one at Palomar and one in Arizona, Palomar Transient Factory and Catalina Real-Time Transient Survey. They use small telescopes, not big telescopes, small telescopes with a wide field of view to patrol the sky many times, look at data, automatically compare the data from tonight to what was there before, look for things that have changed. Our friends in Arizona look for asteroids that may impact the Earth, possibly the most important scientific experiment on the planet. We look for things that go bang in the night, various kinds of supernova explosions, variable stars, accreting black holes, and what have you. And you're dealing with the challenge of processing and analyzing a data stream, not a data set. So you have to react to things as they happen, analyze them, figure out what's interesting, deploy other resources to follow them up. And that involves a great deal of machine learning and actually some brand new research in applied computer science. So an upshot is that we're monitoring 500 million objects on the sky over a period of now 10 years, with time baselines ranging from 10 minutes to 10 years and growing. And there is all kinds of variable stuff. Most of these 500 million things don't do anything. But many of them do. Some of them vary in a very interesting manner. Some just appear out of nowhere and then disappear. And we'd like to catch them when they're hot, and so on. And so this is an unprecedented data set to explore this whole time domain of the universe. You know, we used to think of astronomy, things don't change very fast, but actually there is a great deal of stuff that changes out there. So let's give just some flavor of what kind of stuff we're doing. So in this particular case, we're dealing with time series of measurements, but very ugly time series of measurements. They're non-uniform, heterogeneous, sampling is awful, signal-to-noise varies, number of data points varies, everything varies. These are not textbook examples of time series. We used Fourier methods and what have you. So this requires a different approach. So we have a trick that instead of looking at the data directly, we characterize these messy time series with a whole bunch of statistical descriptors, which contain in principle all information about them. And now we have a homogeneous set of feature vectors, which is what machine learning tools can deal with. And we can then experiment with a variety of many different machine learning tools that Pietro and Yusong mentioned, and other speakers will. And we can classify objects of different nature in this parameter space and look for outliers and potentially interesting things. And we want to do this in real time as the data are coming through with a system that learns as it goes. Let me give you another example. Quasars are interesting kinds of objects. They're powered by massive black holes. They look exactly like stars. And so there is a premium of finding quasars among millions of more stars. And there are many ways to do it, but we use machine learning, combining these parameters we derive from our own measurements of their variability, and measurements from space, from WISE satellite, completely different kind of data, into a joint feature space. And in it, we managed to find classifier that picks them up with 100% accuracy, which is just completely unprecedented. Typically, this was 60%, 70%, 90% in best cases. Nobody's ever done it at a 100% level. We're kind of amazed ourselves. And so this will actually increase the number of known quasars for astronomy by a factor of 2 or more, and enabling all kinds of other science. Incidentally, SURF students help with this. So we characterize how quasars and stars and other things vary. They all vary stochastically, but some vary randomly in a different way than others. So we look for outliers, things that vary in subtly different ways from everything else, and look up what's going on with them. And so we found out that those outliers we selected through machine learning process actually do some interesting things. They change on time scales of years. We typically thought that quasars evolve on scales of tens of millions of years. Well, there are some that evolve on scales of years. They change their physical appearance in spectroscopy and so on. And we're learning some interesting new things, that we can do this now in systematic fashion, not just occasionally run into something strange by serendipity, but systematically look, what is this family of objects doing? I'll be remiss if I didn't talk about LIGO, because what's probably not appreciated is that LIGO is as much computational project as anything else. In 2 ways. They collect vast amounts of data from their detectors and sensors and everything, and finding these chirp signals in this mass of data is actually highly non-trivial. The first one they found was exceptional, that they will never see something as nice and clean as this. It will require a hell of a lot more sophisticated processing to dig up others. So not only is this a data processing issue, but also interpretation of these data critically depends on very sophisticated numerical simulations using general relativity and so on, because that is the only way in which the mess of observations can be actually turned into scientific conclusions about black holes. Well, these are black holes that came from death of massive stars, the tens of times mass of our sun. But there is another kind of black holes. They're 10 million times bigger. They'll reside in cores of galaxies, including Milky Way. Essentially, every galaxy has a big one like that. And our understanding of how structure evolves in the universe is that galaxies merge together in collisions. When they do that, their big black holes will merge, just kind of spiraling together, eventually losing their energy due to the gravitational wave radiation, and merge, just like those in LIGO. Except these are 10 million times bigger or 100 million times bigger. When they do this, they emit bursts of gravitational waves. And the amount of energy is like 10 to 100 billion with a B supernovas going off at once, emitted in a span of minutes or at most an hour. All of it in gravitational waves. And nobody knows what that does to the host galaxies of these objects. How can we find these? LIGO is not going to see these. These are long wavelength gravitational waves, size of solar system, not size of few kilometers. So LIGO operates at kilohertz or lower frequency. These are nanohertz. Well, we found some. By analyzing data from the sky survey, remember 500 million objects, 400,000 of them known quasars, we managed to find a small fraction that show periodic signal superposed on otherwise random signal, like stock market. And so by using combination of machine learning and statistics and a lot of Monte Carlo simulations to find false rate and so on, we found that there were approximately 1 in 3,000 or 4,000 quasars harbors one of these closed binary merging systems. We have never seen those mergers yet, and these that we've seen so far will take some hundreds of years to happen. But they will be detected with satellite networks called ELISA, just like LIGO but in space and much bigger, or with timing of pulsars, where ultra-precise clocks in different directions, and as the big gravitational wave passes through a solar system, it jiggers the arrival times of these pulses. And people at Caltech and JPL are working on this. We think that within 5 to 10 years, we will see those long wavelength gravitational waves from these objects. Now remember, we find things as in real time, things that go bang in the night. The problem is, all of them look exactly the same. Star is brighter now than it used to be before. And they're vastly different physical phenomena. Some of them are a lot more interesting than others. How do we find out which ones among thousands and soon millions per night to select for follow-up with expensive resources like Keck or Hubble and so on? This is where machine learning comes in. This is an extremely difficult problem because data are sparse and heterogeneous and messy. And we play with all manner of different algorithms working with our colleagues at JPL. So I will not go through any of this, but it is something that we're actually making real progress. And basically, we're working towards changing astronomy from something that you go to a telescope, get data, analyze, and think what to do, next proposal, to essentially astronomy of robotic telescopes and computational systems that operate almost without human intervention, because the data volumes are so huge, you want to take humans out of the loop. And so my ambition is to see there in the lower right corner, I want every morning to wake up, get my espresso, log in, and then see what my robots have discovered previous night. And then the next stage is have AI write papers. So, I mean, things are going to get a lot cheaper if I don't have to find money to pay students and postdocs, right? Let me tell you then a few things about our research center, Center for Data-Driven Discovery, which is a part of the joint initiative with JPL, with their own Center for Data Science and Technology. Our mission is twofold. First, to provide research groups at Caltech with the expertise to do this data-intensive, computational-intensive science. But more interestingly, in my mind, is to serve as the methodology transfer device, as the melting pot of ideas and catalyst of new collaborations, whether we can reuse the solutions we develop for one field somewhere else. Because at some point, it's all ones and zeros. At some higher level, it's all feature vectors or databases or what have you. And it doesn't matter whether the data came from telescopes or gene sequencing machines or seismographs or something like that. So can we reuse methodology and saved trouble and time from one field to another? The answer is, of course, yes. So just to give you a few examples, our friends at JPL have developed a fantastic software system called Object-Oriented Data Technology, or ODDITY, which is open source and has got prizes from Apache Foundation, which was developed to deal with data from space observations, but it's been used in fields from medicine, through national security, to geology, to whatever. We have written a paper in Genomics Journal that drew parallels between the data problem of genomics, how to organize and access their data, with Virtual Observatory. It was almost perfect mapping, and for over a month, this was the most downloaded paper from the journal, just as a position paper. We are working with National Cancer Institute on establishing cyber infrastructure for cancer research. There is a branch of National Cancer Institute that works on early detection of cancer, and we help them develop the full data structure and architecture, how you ingest different things, how people access them, and so on. Again, very much like the Virtual Observatory. And we're also conveying this to the Earth Sciences, an NSF program called EarthCube, which basically is building Virtual Observatory for planet Earth. So why reinvent the wheels? Because we already made all the mistakes. Somebody says experience is the name we give to our mistakes, and we're very experienced. But let me give you a couple other examples. How to use the analysis from sky surveys to neurobiology. We're working with Ralph Adolphs in the Brain Imaging Center. And we're applying some of the tools developed to analyze data from sky surveys and high-energy physics to analyze neurobiology data. The first toy problem we played with is the clinical diagnosis of autism. And turns out this is done through questionnaires and what have you before you go to the MRI. And the short story is the questionnaires they give to patients, different kinds, 600 different kinds of questions. Turns out about 6 of them contain all the information. And that was not obvious at all. Everything else is just adding noise to the process. So with 3 different ways that we approach this all kind of led us to the same result. And we can now diagnose autism with almost 100% accuracy on the basis of these traditional techniques, which are by no means perfect. The problem there is not the techniques, but absence of data. Next, we'll be moving in analysis of their MRI scans, which are time series of data cubes. We can learn from them how to actually extract signals from that. We can help them apply things like hidden Markov models and so on to figure out how the brain actually works. And I'm very enthusiastic about pursuing this in the future. You remember the story about detection of transient sources on the sky and then classifying them and figuring out what to do and automatically deciding whether you want to spend your resources on this or not. Well, it's very similar to what seismologists are doing. And Julian Bunn from our center has been working with Rob Clayton and others, trying to use cell phones as seismographs. An individual cell phone is too noisy. Many of them are in motion, some are not. So they figured out software that runs in the cloud that figures out which cell phones to use to average signals, and basically you have distributed seismograph network for free. And the next step is, of course, once you see that earthquake happened there, you can send alert to the subscribers using those very same cell phones that big waves coming in 20 seconds or 30 seconds and duck and cover. So I think that could be a very useful thing in Southern California. Now, one other general need that everybody has in data science is data visualization. And this gets to be a real problem when you're dealing with high dimensionality data sets, as I've been talking about. We can all see 2-dimensional plots on paper or screen. We can even see 3-dimensional plots. What if your data have 30 dimensions, or 300, or 3,000? Now, not all of them are equally interesting, but there is a real premium of being able to see things in as many dimensions as you can, with as high efficiency as you can, to be able to really convey informational content into your brain. Because we have fantastic pattern recognition system in our heads, and we feed that pattern recognition system through the vision. So we've been playing with uses of virtual reality as a new platform to visualize high-dimensionality data sets where things become far more obvious. So scientists can walk into their data and interact with their colleagues and their data simultaneously. And the perceptions of relationships in the data are much more intuitive. Our friends at JPL have tested this with people who drive Mars rover, and they do it 4 times better using VR than they do with traditional panoramic photography. This has also resulted in a startup, Caltech and JPL, is commercializing this. We're getting a great deal of interest from finance industry because even small advantage there can translate into a great gains. So, Deborah, ask me in 5 years. But let me conclude at this. Astronomy, indeed, is being completely transformed with computing and information technology. So is every other science. And so is, in fact, every other area of modern society and commerce and economy. And I think methodology transfer is something we really need to focus on instead of reinventing it. Imagine if every field had to invent their own statistics or calculus. This would be silly. Now, at Caltech, we do have potential advantage of smallness and closeness, and it's so easy to establish these connections. If you told me back in grad school that I'll be working with neurobiology stuff, so that's ridiculous. All right, or geologists for that matter. But this is what's happening. We're building new parts of the scientific method for the 21st century. And a lot of it has originated here and will continue to do so. Thank you.